So as Ashish said, I will be telling you a little bit about Plastic version 2. So this is on behalf of the entire Plastic team, but I want to, in particular, highlight the work that you'll see from Alex Galliano, who's a grad student with me, and Martin Locken, who's a grad student with Rene Classic. So before we jump into what Plastic version 2 is, let's do a quick reminder of what Plastic version 1 is. Plastic version 1 was a public Kaggle challenge where we produced something like 3 million LSST light curves of a whole bunch of different variables and transients in LSST bands. And we set up this Kaggle challenge to really jumpstart photometric ML classification efforts and get new approaches that we hadn't been trying in the community out there. In that respect, Plastic version 1 has just been a tremendous success. We've seen the development of R and N based classifiers. I'm highlighting one here, very recent work by Ashley Villar, who's doing anomaly detection with a plastic data set using variational recurrent autoencoders, a variant recurrent autoencoder neural network. We've seen Daniel Muthukrishna, one of my students, come up with RAPID using ZTF sims that use the same models for plastic. We saw efforts to use things like UMaps for the first time in the astrophysics literature for time domain classification. And interestingly, these came from the general public. They weren't approaches that we pushed initially from within the community. So it had a lot of things that it did well in Plastic version 1, but it did have some shortcomings. And the biggest one is that we gave people flat light curve files on disk and said, here's the full light curve, go off and classify things. That's good if you want to try to get new classification approaches into the literature, but it isn't actually reflective of what's going to happen in reality. So in reality, what happens, of course, is that you don't get the full light curve at once. You instead get alert from some detection, another alert, maybe a day or two later, another alert. And so it looks as like a steady sparse, slowly time evolving source. And you have to classify and make a decision on this kind of data rather than a full light curve. And if you look at this page for 21JAP, which is a supernova that we just started following recently with DECAM from ZTF, it's a supernova that the LSSTC group reported to TNS, and it's important because it's really in an interesting galaxy. The thing that jumps out at you is that what tells you this is an interesting object is in fact not just the entire light curve morphology, because you don't have all of that, but rather the fact that this is a real supernova in a real galaxy. And you can see it in a postage stamp. And Plastic version 1 didn't have that. There's no galaxy information at all. There's no postage stamps at all. And we don't have alerts. We gave people full light curves. So how do we prepare the community, science collaborations and broker teams to actually interact really with LSST data? This is where Plastic version 2 comes in. So if you're a broker team, here is why you should care. The idea for Plastic version 2 is that it really connects what's going to happen from LSST with a broker team. It's a challenge no longer to jumpstart classification efforts, but to connect brokers with the LSST science collaborations. We will generate a much more realistic LSST alert stream that actually preserves things like host galaxy correlations and is a real representative sample of what we expect of LSST. We will send those to the broker teams. Those broker teams will sort of be processing all of the simulated alerts, reporting what they think is happening, sending them back into the Plastic team, which is building infrastructure with the whole Marshall and a Tom setup to sort of do the entire end-to-end analysis as you might with LSST. So this is real, honest to goodness preparation for LSST. And it has two important components in that we are verifying that what brokers say they can do can actually be done. And we are validating all of these ML approaches that we've now gotten from Plastic version 1 with a much more realistic training set. And hopefully we can take all of the ML stuff that's done and push it into use for a real survey that's going on now in the form of ZTF or this DECAM survey that I'm part of, etc. And so it really is trying to sort of close the entire loop. And we envision this as sort of being a little bit iterative in that you can actually do this a few times to ensure this full compatibility and get closer and closer to the truth. So in version 2, we're doing all of the stuff we did in version 1, but in addition, we're adding in host galaxy correlations using CosmoDC2 and a package called Ghost developed by Alex Galliano. And once we have that and we generate simulated light curves as we did in Plastic version 1, we discretize those light curves, chop them up into alerts, add in all sorts of additional extra information, including a background of events that's going off from other sources, such as LIGO. So in addition to the LSST alerts this time around, if you subscribe to Plastic version 2, you'll also occasionally get a simulated LIGO sky map to test how well your entire network can work for multi-messenger astrophysics. And this will go out to all of the broker teams through the UW ZADS interface, which is the same thing that's happening for LSST or for ZTF or for this DECAM survey. So the broker teams are more or less connected with that infrastructure already. And there's a whole bunch of nice little fixes under the hood as well. We have vastly more new models for different kinds of variable stars. So for folks with TVS, this is hopefully of use. We've updated the Delta Scuti and Cepheid models. There's a new improved M-dwarf model in there so that M-dwarfs are hopefully now actually more realistic as a contaminant if you're trying to search for kilonova with LSST. We fixed a lot of the model issues that were in some of the older MOSFET models by replacing them with newer models. And we've updated the kilonova model to match what the Bulla has put out there for us. But importantly, in addition to getting a kilonova light curve in the form of an alert stream, again, you'll also get a LIGO sky map, and the sky map's properties are correlated with what you get in the light curve. In other words, you can actually take both and try to infer an ejecta mass or lanthanide fraction and the observing angle. So pretty much as realistic as we can make it right now. The host galaxy correlations are also really particularly important. The silly way to do things is to simply just stick a transient on any old host galaxy and say, aha, we have gotten host galaxy association, but that doesn't actually reflect reality. Supernovae don't happen in every single kind of galaxy, and there are correlations, tight correlations between what kind of supernova you see and what kind of galaxy they live in. And so we've encoded all of that into Plastic. There are transient abundances for galaxies of different properties. We have hostless transients. We'll have cases where the transient host might actually be confusing for broker teams because it could be associated with multiple potential galaxies that are both near each other. And in addition, instead of just giving people a point estimate for a photometric redshift this time, we're actually going to give you a full photo Z probability density function. So this is also preparing broker teams for how to live in the era of LSST, where you no longer just have a point estimate. So Ghost is under the hood the core library we're using to encode these host galaxy correlations. You can actually go visit the Ghost website already, and it's a collection of something like 16,000 real spectroscopically classified supernova and any kind of information we could scrape on their host galaxies at all. So those are host magnitudes, star formation rate, shape parameters, light profile parameters, and you can see in principal component axis space that different kinds of host galaxies seem to correspond, even in this PCA space, to different kinds of transients. So you can sort of see how these host galaxies look different in their postage stamps and seem to correlate with different kinds of transients that are actually in the sky. So the problem, of course, is that, Plastic version 1 had 3 million light curves, but we haven't seen 3 million transients quite yet. And so we only have a small mismatching number going from 16,000 to 3 million. So there has to be a little bit of work to augment the Ghost sample with your extra galaxies. And this is where CosmoDC2 comes in. So CosmoDC2, as Melissa said, will be up on the Rubin Science platform. It'll be part of Data Preview 0. So you can do all sorts of extra science projects that nobody had envisioned when we were coming up with DC2. And this is kind of actually one of them. If you want to augment galaxies that look like Ghosts, you can essentially take fundamental properties of those galaxies in their S frames and find new corresponding galaxies to them within CosmoDC2, in this case using nearest neighbor. And if you have a large number of nearest neighbors, something like 1,000, then you can go from 16,000 galaxies to a larger sample size, which is what we need for plastic. The problem we found in doing this, and this is where, again, this is a beautiful challenge for validation, is that we found an interesting set of bugs in DC2. DC2 uses the SEDs of galaxies to generate properties. But as you go to higher and higher redshift, the wavelength coverage of those real SEDs is not complete. And consequently, only a few of them are being used to generate properties as you go to higher redshift, leading to some discretization here in color versus redshift, but really in all of the properties. You can try to sort this problem out by using imbalance learn to oversample, but that doesn't work so well. So instead, what we've been using is normalizing flows to essentially get a conditioned set of properties, replacing the ones that have this discretization conditioned on properties that do not have discretization, leading to a much more smooth distribution. So in fact, this effort on plastic version 2 is also helping improve the DC2 sims themselves. We can actually check that after we did all this, we can recover the same sort of ghost galaxies that we put in. And so you can see the original ghost galaxies on the bottom row, and then galaxies that are matched reasonably well from Cosmo DC2. There's still a little bit of discretization there. I think this is an older version of that slide. And I think most of those issues have been sorted out. So the upshot of this is that we can scale up from ghosts with a very narrow peak rate low redshift distribution sample to something that's much more reflective of what LSST itself will find, which is cool. So the whole sort of properties you should expect to see if you're a classifier are honest to goodness GRIZ magnitudes, photos Zs, again as a PDF, the morphology. We hope to include things like a directional light radius and local host galaxy surface brightness properties. So we're working with the LSST alert production team and Eric Baum to actually put these things into alert packet that looks like what LSST will feed you. And critically, we also hope to have posted stamps. We don't think we'll have things like star formation rate and stellar mass because that's a little bit too model dependent. And these host galaxies have a whole bunch of use. Of course, people are really using them right now to decide if a particular supernova are real or not. But you can use the transient separation or these correlations with the environment. You can even push them through something like the LSI stamp classifier to decide if a particular transient that you get out of plastic version 2 is in fact real or bogus. And we totally will be incorporating things like sensor anomaly failures and photometric correction errors and difference imaging errors. And so we see also a way to go forward with this in generating a full simulation, which actually has realistic DIA stamps. For version 2, at least, we'll only be putting out the one template stamp for the host galaxy. But you can see how you can extend this procedure in the future. And then that way we'll also be able to see how brokers handle issues with subtraction pipeline for LSST, issues where we need to know what the flux recovery is as a function of redshift, or what the host supernova is, or what the magnitude is. Things that are basically telling us all about the selection effects of the survey and all the biases that we will measure. So for posted stamps, you can simply use the matched stamps between Ghost and DC2 directly. And you can see you can pick a galaxy in Ghost from PanStars and get galaxies that look pretty darn similar to it already from DC2. But you can actually hopefully do a little bit better. So one of the nice nifty things that we've been playing with is UMAPs, which is one of the codes that we saw a lot of people trying to use in plastic version 1. So Alex Galliano worked with Carlos Scheidecker, who's part of the Antares team at University of Arizona, and they set up a UMAP space that encodes the ghost galaxies that gives you a little preview of a simulated postage stamp with a relatively terrible color scheme here, but you can see how that morphology is changing as you move around in the property space, which is a little bit hard to explain in the case of UMAP since it's a completely non-linear space, but suffice to say that different parts of the space look like different supernovae, and you are getting correspondingly different looking hosts as you move around. All right, enough of keep video. So the current status is that we have most of the inputs set up. We have done some initial generations of simulations. If you care about training sets and validation, you should see the demo from Renee and Alex this afternoon that will show how we can do this all and send that information off to broker teams or people who are building ML classifiers. we're in the process of chunking up our light curves into alerts, and there's going to be a little bit of vetting of all of these things before we send them off to UW and Eric Perm's team, who will make sure that the infrastructure to send those alerts out to broker teams is in place. And then we plan to run this challenge sometime this summer, so not very long. We've already done a first pass of the simulation with something like 16,000 odd light curves. So you can sort of see the LSST wide fast deep footprint on the sky with different redshifts for our simulated sample, again, matching from Cosmo, DC2, and Ghost together. So the host galaxies in here for our transients really look like the host galaxies of actual supernovae. And critically, broker teams might care about this because in addition to doing this for LSST, it is possible to generate these simulations for other surveys, including surveys that are going on right now, like CTF or this DECAT survey or the Young Supernova experiment that I'm a part of. If you're interested in doing some of this stuff, come talk to the PLAsTiC team. We would be happy to help you. So essentially, I want to sort of end up with what PLAsTiC can do for you. So it's a framework that's really generating the photometry and spectroscopy and transients and hosts. So it's really a time domain simulation of the entire sky. We've gotten a whole bunch of new models in there, and we're trying to make these simulations look a lot closer to reality, because simply we're never going to find enough kilonova in the real survey to get us ready for LSST in time. We have to rely on simulations here. And we have to therefore make those simulations as good as possible. If you're a broker team and you want to use PLAsTiC as a training or a validation set for any of your wide field surveys that's ongoing or upcoming, let us know. And the goal here is really to connect the science collaborations of LSST and the broker teams and get these groups that are doing great work independently to actually work together. And I'll stop there and take questions.
Great, thank you for finishing in time, Gautham. There is one comment and one question on Slack channel. Franz Bauer asks, are the M-dwarf flare models input as repeating or singular? Same question for CV, and if they're repeating, on what timescales?
So the M-dwarf flare model can repeat. The current version of the model is built off of a combination of Kepler and test data. We've taken the Kepler light curves for these M-dwarfs. We have a model for T effective of the star versus T effective of the flare. And so we use a black body to model to transfer from the Kepler amplitude to amplitudes in all of the LSST bands. Let us know if this is not going to work. There's, as part of this model, of course, we have all sorts of distributions. What the sort of typical amplitude that we see in Kepler is, to draw from what's the sort of typical T effective temperature of the stars to draw from, but also how frequently these stars have repeat flares. And so we can put in events that have multiple flares or just a single flare as part of the model. It's fairly flexible. If you're interested in details of this model, it's being built by an undergrad, a really talented undergrad here at UIUC, which along with my postdoc, Konstantin Melanchev, would be happy to work with.
Great, thanks. Michael, what about the... Sorry, you had a follow-up question?
Just what about the CVs?
The CVs, so there is an existing CV model in PLAsTiC version 1. I have not updated that in any way. We thought it worked pretty well. We knew we wanted to improve the M-dwarfs largely because people were classifying them incredibly perfectly and without any confusion to LSST. And we realized that this was really just a fundamental drawback in the simplicity of the model that we had last time around. So okay, there is a CV model.
Okay, so there are more questions coming there. We may not be able to get to all of them. So let me ask quickly the one that asked about, you have simulated data in PLAsTiC. So when people use it, how can they compare it with real world data? Are there ways to do that for them?
Yeah, absolutely. There's totally good ways to do that. So like I said, you can simulate in other surveys as well, and we have done. And so one of the simulations we've shared fairly widely has been a simulation of light curves as to how they should look in CTF. And ZTF is going on right now, so you can compare them directly. So one of the things we do, for example, in my group is take real supernovae, type 1a supernovae, from both ZTF and our simulated data, get close by in sort of like 0.1 redshift bins matches, align them up at peak and see how they look and make sure that this simulation actually looks like reality. We also can do this as a function of rates for different models, seeing if the relative frequency of things that CTF is detecting matches what we put into the simulation. So there's a lot of that internal validation work that has happened to get you sims with high fidelity, but you can do a whole bunch of other experiments by simply taking the sims and comparing them to reality for whatever particular class you care about.
Yeah, great, thanks. There are other nuances to the question also, so do take a look at the Slack channel and answer them there. I wanted to make a quick comment about UMAP. It seems great that you're using it, but I'm sure you know that the UMAPs can be very dicey in the sense that when you have a slightly different distribution, their 2D distribution also changes. So when we go from one set of simulations to another, that can change. And
so like we said, we have two ways of getting twisted stamps. One is UMAP, the other is just relying on Cosmo DC2, which is slower, but probably more safe.
Great, thank you.